Okay, so for this circuit, we have to find the voltage at this capacitor. So we're going to view the circuit when t was less than 0. So when t was less than 0, this switch was closed. So we had the following. Okay, and we're assuming that the circuit looked like this for a long time. So pretty much this becomes a closed wire. Short circuit, so it becomes a closed wire, and this becomes an open circuit. So we have 3 amps traveling through here. We have 20 ohms, and then we have a voltage here. So right now we need to find the initial voltage. Sorry, we have to find the voltage at this region. So we see as current travels through here, it's gonna pretty much skip this wire. It's not gonna travel through it because it'll notice it has this wire it can travel through instead. So we can practically, because this wire has no resistors, and I'll choose the path with no resistors rather than choosing a path with resistors. So that means that resistor is pretty much useless, and we'll only have current passing through here. Okay, so that means there's really no voltage. So that means this is going to be just 0, and so that means V of 0 is going to be 0. Okay, so because the voltage at a capacitor can change instantaneously. So the second when t is equal to 0, the voltage at the capacitor is still going to be 0. Now let's look when t is greater than or equal to 0. And when that happens, this switch is open. So that means this part of the circuit is useless. So we just have the following. So this is 20 ohms. This is 10 henries. And this is 0.004 farads. Okay, and V here. Okay, so hold on, let me draw this perfectly. Okay, there. So the voltage at this capacitor is pretty much going to be the same voltage for this whole region. Okay, so I'm going to put V to be here. Okay, so what I'm going to do now is do a node analysis. So this is I1, I2, and I3. So to find the current for this one, it's just going to be V over 20. Okay, then for this one, actually let's do this one first. This one is going to be the capacitance of the change in voltage over the change in time. And for this one, the current passing through here is going to be 1 over L times the integral of V dt plus I then at 0. So sorry, the initial current. Okay, so this is pretty much the node equation at this region. So I don't like this integral, so I'm going to get rid of it. So I'm going to differentiate this whole thing. So it'll be 1 over 20 times v over dt plus c d squared v over dt squared plus 1 over L times v. And this is a constant, so this is just going to go away. So let's just, and we're going to divide everything by c. Okay, so it's going to be d squared v over dt squared plus 1 over 20 c dv over dt plus 1 over lc times v. Okay, now I'm gonna have the I'm gonna have dv over dt be equal to s, so it'll be s squared plus 1 over 20 c s plus 1 over lc. Now I'm gonna use the quadratic formula to solve for s, so it'll be minus 1 over 20 c plus minus the square root of 1 over 20 c squared minus 4 ac, a being 1, so and c being 1 over lc, all over 2a. Now break this up. And this is just the same thing as this. And this, I could take the square root of 4, which is still 2, and embed 1 square root into all of this. Break this up. This and this cancels out. And this, I can put it in here if it's a 2. There you go. Then this is gone. And this part, I can square root all of this and square it at the same time. So it'll just be 1 over the square root of LC. Okay? Now this is going to be alpha. This is alpha. This is omega. Okay? So alpha is your damping factor. Omega is your undamped natural frequency. So it'll be minus alpha plus minus alpha squared minus omega squared. Okay? So your alpha should be equal to 1 over 2 times the resistance times the capacitance. And then your omega should be equal to 1 over the square root of LC. So this is going to be 1 over 2 times 20 times C, which was 0.004. And this is equal to 6.25. And this is equal to 1 over the square root of LC. So L was 10 times 0.004. Okay, and let me see what that gives me. That gives me 5. And these are in radians per second. Now we have to check the following. So if alpha is greater than omega, then it means it's overdamping. And to find the voltage passing through the capacitor, it's going to be A1 E S1T plus A2 E S2T. S being this S1 and S2 being the roots for this. So when alpha is equal to omega, it's going to be critically damping. So the voltage passing through the capacitance will be A1 plus A2T times E to the power of minus alpha T. Now if alpha is less than omega, then it's under damping. So it will be Vt equals E to the power of alpha T times A1 cos WDT. WD being the damping frequency, which, if omega is greater than alpha, then that means you're going to get an imaginary value. And whatever is being timed by that imaginary value is your WD. The plus A2 sine WDT. Now we're going to see which one we should be using. So we see our alpha is greater than our omega. So that means we're going to be using this one. So let's find our roots. So our S1 and S2 is going to be equal to minus 6.25 plus minus the square root of 6.25 squared minus 5 squared. So S1 and S2, let's see, those are respectively going to be equal to minus 2.5 and minus 10. Okay, so Vt will be equal to A1E minus 2.5t plus A2E minus 10t. Now we have to solve for A1 and A2. So we know when t was 0, our voltage was 0. So we can just do the following. Okay, so that means A1 will be equal to minus A2, or minus A1 is equal to A2. Now let's differentiate all of this because right now we only have one equation and we need two equations, and we have one equation and two unknowns, and we need two equations. So let's differentiate everything. Okay, so now we differentiated all of this. Now we have to find dv over dt at a specific instance. So let's see what we can do. We see if we view this when t was equal to 0, we know the voltage here is 0. Now we just need to find the value of this current. Okay, so we see that when t was less than 0, obviously this region was pretty much where our inductor was, and we see that 3 amps was traveling through here. And since the current passing through an inductor can change instantaneously, the second t is equal to 0, the value of all of this should be also 3 amps. So that means it's 0 plus c dv over dt plus 3. So it'll be dv over dt equals minus 3 over c, c being 0.004, and that gives you minus 750. So it's going to be minus 750 equals minus 2.5 A1 minus 10 A2. Okay, and this is gone because these are now to the power of 0. And recall A1 is equal to minus A2. So this and this cancels out. So minus 750 equals 2.5 A2 minus 10 A2. And that means A2 will be equal to 100. And that means A1 is equal to minus 100. And now we can find Vt, which will be minus 100 e to the power of minus 2.5 t plus 100 e to the power of minus 10 t, and that's in volts, and that's the voltage formula traveling through the voltage formula for the capacitor.